So up until now, we have been assuming that we always have enough of each of the reagents that we're going to be able to consume all of one of the reagents. We've always been talking about having an excess of one reagent, and that's going to mean that we're going to use up all of another reagent. Now that reagent that we use up is called our limiting reagent. It's going to dictate how much of something that we ultimately can make, because once it's consumed, the reaction won't go forward. So sometimes we don't have enough of one reagent for a complete reaction. We will have some of the reagents left over, right? So if I have one thing and a ton of excess, and I use up all of this and the reaction stops, I'm going to have some of this other excess stuff left over. We must determine which is the limiting reagent in this case. So we have to know which one is going to be in excess and they're going to have some left over, and which one we're going to be able to totally consume. Now this is a little silly, but I made like kind of a silly example to first kind of step us through how to do limiting reagents. So let's go through this here. So a ham sandwich is made with 2 slices of bread, 1 slice of ham, and 1 slice of cheese. How many sandwiches can be made with 7 slices of bread, 3 slices of ham, and 4 slices of cheese? How many ingredients are left over? So the first thing that we're going to do is we're going to calculate the number of sandwiches that we can make with each ingredient, assuming that that all the other ingredients are in excess, assuming that we have more than enough of the other ingredients. Which one of these is going to limit the total number of sandwiches that we can make? So if I have 7 bread, and for every 1 sandwich there's 2 bread that's required, then I can do a conversion to sandwiches from bread. I cancel my bread, and I can see that I can make 3.5 sandwiches. If I have 3 ham, there's 1 ham per sandwich. We cancel ham. We can see that we have enough ham to make 3 sandwiches. I have 4 cheeses. I cancel my cheeses, and I can see that I have enough cheese to make 4 sandwiches. So the limiting reagent is the smallest one. The ham is what's holding me up. I can only make 3 sandwiches with the amount of ham that I have. So it doesn't matter how much more bread or cheese I have, I can't make a sandwich if a sandwich has 1 slice of ham, 1 slice of cheese, and 2 pieces of bread. So we can see now that ham is our limiting reagent. We only have enough ham for 3 sandwiches. So now we can calculate the ingredients consumed in the making of 3 sandwiches. So we know now that we're making 3 sandwiches. Let's see how many bread we're going to use, how many ham, how many cheese. So in we got 3 sandwiches. We need 2 bread for every sandwich. We're going to use up 6 bread. We're going to use up 3 ham, and we're going to use up 3 cheese. So with that knowledge, we can now calculate the amount of ingredients that remain. So we have 7 bread. We're going to use 6 of them to make our 3 sandwiches. We're going to have 1 bread left over. We have 3 ham. We're going to use up all 3 of those ham. We're going to have 0 ham left over. We have 4 cheese. We used up all 3 of the cheese. We're going to use up 3 cheeses. We're going to have 1 cheese left over. Notice that our limiting reagent is at 0, as it should be. We're using all that up. That's what's holding us up in the first place. Okay, now that we've gone through our silly sandwich example, let's take a look at a real example using chemistry and chemicals. What mass of sodium chloride would be produced from the reaction of 10 grams of sodium metal and 20 grams of chlorine gas? So there's a lot of language here that seems a little unfamiliar, but it's really pretty much the same as our sandwich example. There's only one or two extra steps that we need to do, and they're right at the beginning. So the first thing we need to do is write out our balanced equation for this reaction. We can see that there's going to be two sodium metals. It's going to react with diatomic chlorine, and it's going to produce two sodium chloride molecules. Now, we know that we can make our different ratios that we're going to need, just like 2 bread for every 1 sandwich, out of these guys. But that this is telling us molar ratios, and we've only been given masses so far. So the first thing that we need to do that we didn't need to do in our sandwich example is calculate the number of moles of each of our reactants. So first we'll start off with the sodium. We had 10 grams of sodium. If we look it up, there's 22.990 grams of sodium for every 1 mole. We do the math out and we get 0.4350 moles of sodium. Sodium was just an element, atomic element that was put in there, so we didn't really have to calculate a formula mass for it. But chlorine is a molecule, so we're going to have to calculate a formula mass for that. We know that we have 2 atoms of chlorine, so this formula mass is going to be 2 times the atomic mass of chlorine, or 2 times 35.453 AMU. So 1 chlorine molecule weighs 70.906 AMU, or 70.906 grams per mole of chlorine gas. It's important that you always calculate the formula masses, because that's what the ratios are going to be for, right? We're not saying that we're going to have 2 atoms or 1 atom of chlorine for every 2 moles of sodium. We're saying that we're going to have 1 diatomic chlorine here. Now we can calculate how many moles of that molecule we have. We take 20.00 grams, we divide it by the formula mass, and we see that we have 0.2821 moles of the chlorine. So next we need to calculate the number of moles of sodium chloride produced by each reagent, again assuming that the other reagent is in excess. So we take the moles of sodium and the moles of chlorine that we just calculated, and we multiply them by their stoichiometric coefficients. So we saw that there's going to be 2 NaCl for every 2 moles of sodium chloride. I'm getting that from the formula here. There's 2 moles of sodium chloride for every 2 moles of sodium. And therefore, this many moles of sodium chloride would produce the same number of moles, because, 2 divided by 2 is 1. We're going to cancel our moles of sodium. And we're going to have 0.4350 moles of sodium chloride. We're going to do the same thing for the chlorine molecules. Again, remembering that now we have a different stoichiometric ratio. There's an assumed 1 right here. And so there's going to be 1 mole of chlorine gas consumed for every 2 moles of sodium chloride we produce. And we do that math out, and we get 0.5642 moles of sodium chloride. So, just like before, where we could only make 3 sandwiches with our ham, we can make only 0.4350 moles of sodium chloride with the amount of sodium that we have. It is our limiting reagent. Now we can calculate the amount of reagents consumed by the reaction, assuming complete conversion. Just like before, or we've already figured out that we're going to consume all of our sodium, right? That's going to be the 0.4350 moles, or all 10 grams of it. But we're only going to consume part of our chlorine. And the way that we figure out how much we're going to consume is we're just going to use our stoichiometry. So we have 0.4350 moles of sodium reacting. We're going to have 1 mole of chlorine gas for every 2 moles of sodium. Again, I'm getting that from here. We have 2 for the sodium and a 1 up here for the chlorine gas. And when I cancel these units, I can see that I'm going to get 0.2175 moles of chlorine gas. Now, I'm likely going to be interested in how much mass that is. And I can get that by just taking those moles and multiplying it by the molecular weight that we already determined for chlorine gas before. We know that there's 70.0 or 0.906 grams for every 1 mole of chlorine gas, which comes to 15.42 grams, which makes sense. It is less than the 20 grams that we know that we had. If it was greater than that, then that wouldn't make any sense. So now that we know how much was consumed, we can calculate the amount of leftover reagents. So the amount of leftover sodium is 0, right? We said that our limiting reagent, we're going to consume all of that. And since we know how much we consumed of the chlorine, we can see how much is left over. So we started off with 0.2821 moles of the chlorine gas. That was the very first thing that we calculated. Right down here. That 20 grams is going to equal that many moles of the chlorine gas. We said that we were going to consume 0.2175 moles of the chlorine gas. We subtract the amount that we started with minus the amount that we consumed, and we can see that there is left over 0.0646 moles of chlorine gas. If we want to know the mass that was left over, we could take this number of moles and again multiply it by its molecular weight. Or we could even be clever, because we've already done some of this math, and say we started off with 20 grams of chlorine gas. We're going to consume 15.42 grams of chlorine gas. So the amount left over is going to be 4.58 grams of chlorine gas. Finally, we can calculate the mass of the product produced. So first we need to know the formula mass of NaCl. That's going to be the mass of sodium plus the mass of chlorine. And when I add those two together, I'm going to get 58.443 grams per mole of sodium chloride. I know that I'm going to produce 0.435 moles of sodium chloride. I calculated that at the very beginning. I'm going to multiply it by that formula mass, and I'm going to see that I produce 25.423 grams of sodium chloride. Now, what should be true is that if I calculate the mass of sodium, this should be the mass of sodium that is that we consumed plus the mass of chlorine that we consumed. So 15.42 plus . 10 grams is in fact the same. 10 plus 15.42 is 25.423 grams. Now, if you guys are very astute, you may realize that we did not need to calculate the amount that was left over or the amount that was consumed of our reagents. We could have skipped directly from knowing the number of moles of sodium chloride that we were going to produce and then multiplied it by its formula mass to get to the answer of the question initially. But I do suggest that you guys try to go through these steps for the first couple problems that you do of this sort in order to kind of get a feel for them.